actually a picture of every star in the universe. The interesting thing about this picture is that we now know, of course, I said it before, the color of a star is totally dependent on its mass. The starting mass that it begins with, when it forms, most stars never gain any more mass. In fact, most stars lose mass throughout their lifetime. And the amount of mass that they have determines their color, it determines the position on this diagram. Now, does anyone have a laser pointer? No laser pointer. Alright, well you will see in this diagram, from the top left to the bottom right, a diagonal line. Want to see it? Good. This is called the main sequence. This is where stars begin their journey of nuclear fusion. Now, a lot of really interesting stuff happens to stars while they're fusing hydrogen and for the rest of their evolution. This talk isn't going to concentrate on that at all. I should probably stop saying this talk because, you know, soon we're going to be at the end and then I'm still going to be saying this talk as if there's more to come. What I'm going to be talking about is what happens after this sort of development of stars. And of course, when we talk about stars, we talk about a really useful naming procedure. We use, in the past, it was really simple to look at the spectra of stars. It was really simple to look at the light from a star put through a prism or a diffraction grating and broken up into its wavelengths and its intensity. It was really easy to say, okay, well that star is different to this star and this star is the same, so they started putting them into categories. They didn't know how these categories were arranged. In fact, at the time they thought that the categories were different ages of the stars. So one star would go through all the categories. We know that's not true, like I said before. Now we know it's all mass. The funny thing is they started naming the categories A, B, C, D, E, F, G, you know, pretty normal. Unfortunately, when they rearranged the categories, they kept their original names. So now we have the excellent process of naming these stars from hottest to coolest, from bluest to reddest, from largest to smallest, O, B, A, F, G, K, M. Which is it's really funny, actually. So this is a picture showing you just how different these stars look, just how different they are in size. And I'm going to be talking about the very smallest stars of the universe. For interest, our star is a G star. It's very ordinary, which is interesting. And it's actually especially interesting to our talk. Just for interest, I'm sure you're sitting there thinking, well, just how common are these stars? If you're an O star, you are 1 in 3 million in terms of stars. Only 1 in 3 million stars is an O star. O stars are the rock stars. Okay? They're the ones that live fast and die young and form black holes. massive explosions of their life. You know? It's yeah. Our star's not going to do that. That's okay. Going all the way through, so to be an O star, you have to have more than 16 times the mass of the sun at formation. Going all the way through, let's talk about a G star. To be a G star, you have to be between 0.8 and 1.4 of the mass of the sun. So that makes sense. Of course, I'm talking about units that are compared to the mass of the sun. Funnily enough, our star, a G star is 1 solar mass. If you want to convert it, I said it before, 2 times 10 to the 30 kilograms. If you want to take that home with you. Now, if you're a star like our sun, you're much more common. You're now 1 in 13. Now, if you're the smallest sort of star in the universe, you're an M star, your mass is less than 0.45 the mass of the sun, and 3 out of 4 stars is exactly like you, which is interesting. The universe is full of low-mass stars. And so, when we talk about things like black holes, and supernova, and neutron stars, and all of this fantastic stuff, we're actually not talking about most of the stars in the universe. So, the whole idea of this was to, you know, give the little guys a bit of credit here. So, where are we going to go with this next? No, okay. I've got a fact for you that I forgot to mention before. You know the cloud that we were talking about, the cloud that formed stars, the giant molecular cloud? This thing at the beginning was about 17 times as big as the distance from here closest star, Proxima Centauri. So some of these giant molecular clouds are 17 parsecs in radius. It's incredible. These things are gigantic. They're like stars are huge, but these things are just monstrous by comparison. Of course, they're dwarfed by galaxies. This puts in perspective just how large these things actually are on a human scale. So, well, you know, there's a lot of stuff that we could talk about when we're talking about fusion. There's a lot of stuff we could talk about when we talk about the evolution of stars. But we don't have time for that. So what we're going to do, we're going to skip a few years. We're going to jump ahead into the future of these baby stars that we just saw formed. We're going to jump ahead 10 billion years. So here we go. In fact, most of our stars, most of our low mass stars now look like this, which is interesting. Now, I'm sorry, you know, in our haste doing this 10 billion year time jump, we have unfortunately missed every single supernova. I'm sorry. We've missed every single star which is going to turn into a black hole. It happened almost instantaneously. It actually happened in the first million years, so they are long gone. Interestingly enough, you know, if we compared that 10 billion years, this standard main sequence low mass stellar lifetime, to a human lifetime of 100 years, well, let's put this in perspective. So what am I talking about? Okay, for every second in your life, if you are lucky enough to live to 100, a star would live 3 years. Now that doesn't seem like very long. Well, let's put that in terms of a year. A year in your life then becomes 94,608,000 years for the star. Now if we're talking about dog and cat years, star years got those beat by a long way. So what happened while we were off, you know, while I was talking for the last 10 billion years? What happened to the low mass stars that are still around, like the ones that I have on the screen? Well, a bunch of stuff happened. And we might get to a picture of that. To be perfectly honest, I expected it to be this picture. So that may come. This is kind of exciting. I'm not sure where we are. That's all right. It doesn't matter. The pictures were boring anyway. If they come back, we won't even look. It's all right. Okay, let's speed this up. What happened? Well, we burned hydrogen to helium. We started with a hydrogen core. We started fusing that together. We started forming helium. What else happened? Well, that core, as it was forming helium, increased its density. And then, to sustain the star in hydrostatic equilibrium, it had to get hotter. So, in the last 10 billion years, all of those stars that are still around are denser, they're bigger, they're redder, they're also hotter. Now, the funny thing is that we start off with just a centrally condensed hydrogen core, but as we produce more and more helium, we don't yet, at this point, have the ability to burn that helium into a heavier element. We don't have the ability to start forcing the helium together. So it just sits around. And it's heavier than the hydrogen, so it sinks to the middle. So in the end, we move through a process of actually having a helium core with a hydrogen burning shell around it. Now, interestingly enough, this causes the hydrogen to become more and more energetic with its nuclear fusion. It actually causes more luminosity, more energy to come out of that shell than we had when the whole core was actually burning hydrogen, which is kind of fun. Where are we now? Okay, so well, that's basically about it. Not for the talk. I'm glad that we went, yay! That's good. Thank you for controlling yourselves.